Chapter 14, Kinetics, is what we're going to be talking about today, and we will be hitting section 14.1 and section 14.2 in this lecture, and you should read both of those when you have time. Let's start off with a definition of what we're talking about here, and we're talking about the idea of kinetics. And kinetics really is the study at which the rate a chemical process occurs. Simply stated, how fast does a chemical reaction occur? How slow does a chemical reaction occur? Rate is typically given in the reactants coming together or decomposing, whatever they're doing, and producing products. And we're going to measure it typically, but not always, in concentration over unit time. And so we know for concentration, we typically talk about molarity. So we use molarity, capital M, which is going to be moles per liter. And for time, we typically talk about seconds, although sometimes we might measure things in molarity per hour, and for some really slow chemical reactions, maybe molarity per days or molarity per years. But typically, our molarity per second and molarity per hour is really how we're going to measure how fast a chemical reaction occurs or how slow a chemical reaction occurs. And we want them to occur fast sometimes. In the case of, let's say, some painkiller that you have a headache and you want to take something, you want that to get into your body quick as possible so that you can get rid of that headache that you have. And sometimes we want reactions to occur a little bit slower with respect to medicines, maybe an allergy medicine. If you have allergies in the springtime or something like that, it's going to be a slow release medicine that lasts 12 hours or longer. So chemical reactions can occur fast or slow, like we said. Fast in fireworks, really slow would be rusting of some metal when it's exposed to oxygen. Okay. And we typically talk about these two things in a couple ways. Like we said, we're looking at reactants and products in a chemical reaction, reactants and products. And so when we have a forward reaction going, a reaction that's going from the left towards the right, we talk about what disappearance of reactants, because the reactants are disappearing, they're getting used up or consumed. And we talk about the appearance of products in molarity per second or molarity per hour. Okay, so that's really what the whole study of kinetics is all about, how fast chemical reactions go. Okay, so let's jump into 14.1 now, and these are going to be some of the factors that affect chemical reactions. These are the things that affect how fast a chemical reaction goes or how slow a chemical reaction goes. So the first one is going to be the physical state of the reactants. In order to react, molecules must run into each other. They've got to come into contact with each other in order to react. If they don't come in contact with each other, they're not going to. When you have more homogeneous mixture of the reactants, the faster the molecules can react. So giving another example of that, let's say if we wanted to react a large chunk of some metal, I don't know, let's call it magnesium, a big huge chunk of magnesium, and let's say this guy was 10 grams and we're going to react it with something, versus a ton of tiny little particles that we've ground up, all ground up into a pile, and this was also 10 grams of magnesium. We would expect the small particles to react faster because there's more surface area than the one big chunk of something. And so powders are going to react a lot faster than solids as well. Another thing that affects how fast a chemical reaction goes, or a reaction rate, is the concentration. As the concentration of the reactants increase, usually what happens is the molecules are going to collide more often, and we're also going to have faster reactions. And so here's an example of this. Here's an example of this. And what we have here is we have steel wool. Steel wool is being held, in this picture here, being held over a Bunsen burner, and it's burning. You can burn steel wool. There is a presence of oxygen. You have to have oxygen gas, and that's just going to be oxygen gas that's present in the atmosphere in relatively good enough percentages for us to live and to burn steel wool. But if we have a very high concentration, in this picture we have a high concentration of oxygen gas in an Erlenmeyer flask, and we put the steel wool in there, it's going to immediately just spark and burn very, very, very quickly, because we would say that the concentration of oxygen, and brackets. These brackets are used to denote concentration. The concentration of the oxygen is much higher inside this flask than the concentration, once again in brackets, that is just in the atmosphere, which would be somewhere around 20%. Okay, so increasing the concentration is going to increase how fast a chemical reaction is going to occur. Let's talk about temperature here really quickly. We know just from general chemistry that oftentimes when you have higher temperatures, chemical reactions are going to happen faster. And this is why we use a refrigerator. We want to slow chemical reactions down. We want to slow the spoiling of food down, so we put things in a refrigerator to keep it cold, but also to keep it from spoiling. When you have higher temperatures, you have a greater kinetic energy. Molecules move faster, they collide more with greater energy, and you're going to have faster chemical reactions. The fourth thing that's going to affect the rate of a chemical reaction might be the presence of catalysts. And we talked about catalysts a bit before. These are a substance that are going to speed up a reaction. They change the mechanism of the reaction, and we'll talk more about what a mechanism of reaction is later on. But they change the course that the reaction could take, and they're not consumed. They're not consumed in the course of a reaction. Oftentimes catalysts, like let's say if we catalyze the reaction of hydrogen peroxide into water and oxygen gas, we might catalyze this reaction with manganese dioxide. And we'll write manganese dioxide on top of the arrow just like this, although sometimes we'll write it in the reactant and then we'll write it again in the product unchanged. It's a catalyst. It does not get used up. And then at the end, we could recollect the manganese dioxide and just reuse it over and over again because it's still present. It doesn't get consumed. This, of course, is an unbalanced chemical equation right now, but I'm not going to worry about balancing it. I'll let you do that. Now, there's a graph here showing an uncatalyzed reaction. So if you're starting here, this is our reactants here, and then our products are over here. An uncatalyzed reaction, just a normal chemical reaction, you've got to give it energy. Energy's got to increase to get that reaction to go by itself. And once that reaction is going by itself, it's all a downhill slope, and we're going to give off energy. Now, and this is a typical graph of an exothermic reaction when the reactants are higher than the products. The energy that we put in, we call it activation energy. Now, for a catalyzed reaction, it has a different pathway, often with a lower activation energy. We don't have to put as much energy in to get to our peak, and that's why the catalysts are used to alter the course of a chemical reaction. Well, they don't alter a course, but they definitely change the mechanisms of the reaction, make reactions go faster. Hydrogen peroxide typically doesn't decompose very quickly, but you throw some manganese dioxide in there, that catalyst that we talked about, and it's going to decompose real rapidly. So let's get into 14.2 now. And 14.2 is all about reaction rates, how fast chemical reactions occur. So reaction rates are measured in concentration of reactants or products per unit time, like we said before, typically in molarity per second, maybe molarity per hour. Those are the typical units. And let's say we have this chemical reaction. We have a reaction of A as our reactant, and it's going to be going to be our product. Okay? So down here we have a little diagram, and on this diagram it shows we are at what we would call time zero. Time zero. 0 seconds on the clock. We put some molecule A, and there's a bunch of these molecules in there, and let's say for ease and simplicity, all of these are 1 liter containers. Now, there's a reason for that, and I'll talk about it in a moment. But time zero, we have 1 mole of A, and you can see inside there is no B, because B is actually blue and A is red. We put it in there, we put the top on, and we start the clock, and at 20 seconds, you can see that there's some blue showing up here. We still have A, but we also have some B. So we have now 0.54 moles of A and 0.46 moles of B at 20 seconds. So this reaction is proceeding forward. It is going from the reactant A to the product B. At 40 seconds, we can see that there's a lot more blue, which is B, than there is A. And so now we're down to 0.3 moles of A and 0.7 moles of B at 40 seconds. Okay? So we can see this reaction is progressing forward. Now, what we can do is we can use this data to calculate the rate of appearance of B, the rate of appearance. And this is something that you'll need to know how to do. So let's talk about this. So if we're going to calculate the average rate of appearance of something, and this is of a product, call it average rate of appearance, and we'll say of B, and I'm abbreviating some things. What this is going to be our change in our concentration of B over our change in time. Okay? So what we'll do is we will do the concentration of B at time 2, subtract the concentration of B at time 1, and then we're going to go time 2 minus time 1, because those both give us change of what's going on here. Now, the reason I made this a 1 liter container is so I could talk about molarity easily, because remember, molarity is moles per liter, and if it's a 1 liter container, if I have 1 mole, I have 1 molar. So it's 1 molar. So let's kind of scroll down here just a little bit, and so what we can do is we can plug in some concentrations. So B at time 2, we're gonna say time 2 is at 20 seconds, and so we're gonna say 0.46 molar minus 0.0 molar, and then we're going to do time 2, which was 20 seconds, minus time 1, which was 0 seconds. Okay? And when I divide those two, or when I do the subtraction and the division, I'm going to get an answer of 2.3 times 10 to the negative second molarity per second as our rate of appearance, or average rate of appearance of B. Okay? Now, let's talk about the average rate of disappearance of A. And we're going to do it the same way. We're going to do the average rate of disappearance of A is going to be equal to negative, and it's negative because it's disappearing. And we're going to say it's the change in concentration of A. Remember, concentration is just molarity over the change in time. Okay? And so what we're going to do is we're going to pick the same 2 time intervals. We'll pick 20 seconds and 20 seconds and 0 seconds. And then we're going to plug in those concentrations. So the concentration at 20 seconds for A was 0.54 moles per liter, or 0.54 molar, minus 1 molar, which was the starting concentration. And remember, this is going to be a negative value. So when I do the math here, and I've got 0.54 minus 1, it's going to give me a negative value. But then because we're losing it, it's a negative value as well. And so the answer is going to come out positive, 2.3 times 10 to the negative second molarity per second. And rates are always given in a positive value, even though we know we're losing A. We're losing our reactant, and we're gaining our product. Now, so there's our answer for the average rate of disappearance of A, and we've got our answer for the average rate of disappearance of appearance of B. Now, sorry about that. There's always got to be a bell sometimes in one of these videos. Now, why are these two values equal? Well, the values are equal because of stoichiometry. Remember, we have A going to B, and it was a 1-to-1 ratio. So the rate of disappearance of A is equal to the rate of appearance of B. Now, it's not always that way. We know that we oftentimes have coefficients in balance equations, and so let's talk about how do we use stoichiometry to find out what's going on here. So we have here we're going to use stoichiometry to find rates of disappearance or appearance, depending on what they give us. And so we have a balanced equation. O3 is ozone, and I didn't write that right. I'm going to erase that. It looks like I wrote something completely different. Okay, we'll write that O-Z-O-N-E, ozone. Now, ozone we know is in the upper atmosphere, protects us from UV light from the sun, all those things. It's also produced down, electrical currents going through the air. And oxygen, O2. So we have a 2 to 3 ratio going on here for ozone being decomposed into oxygen, a 2 to 3 ratio to give us a balanced equation. Now, it says, if oxygen gas, in our example, if oxygen gas appears at a rate of 6.0 times 10 to the negative fifth molarity per second, what rate does ozone disappear? So here's how we're going to set this problem up, and we're going to use stoichiometry formula. So we're going to put our known down here, 6.0 times 10 to the negative fifth molarity per second. And now this, remember, is going to be for oxygen. And then we're just going to use a ratio, the mole ratio, from the balanced equation. So oxygen, of course, is going to be on the bottom, so we can cancel out the oxygen. And so from the balanced equation, we have 3 moles of oxygen. And then obviously ozone, which is what we're looking for. We're looking for ozone. And so we have 2 moles of ozone being placed on top. So it's a 2 to 3 ratio. So we just multiply 6.0 times 10 to the negative fifth by 2, and then we divide it all by 3. And so we're going to get an answer of 4.0 times 10 to the negative fifth. Moles and moles are going to cancel, and we're left with molarity per second. And so that is going to be the rate, the rate at which ozone is disappearing, and this, what was given in the problem, is the rate at which oxygen is appearing. And you can see that these two rates are not equal, and the reason they're not equal, of course, is the stoichiometry of a 2 to 3 ratio. Okay, and so that wraps up 14.1 and 14.2. I highly recommend that you read about those and do some of the sample problems in the gray boxes in the textbook.